and today we're going to be talking about radiation. Now, when I say radiation, I'm not necessarily talking about Homer Simpson, nuclear power plants, nuclear bombs, Fukushima, or anything like that, though that kind of stuff is one type of radiation. But there's many other types of radiation, as you're going to see today. Now, a few goals that we have today are to understand the key properties of radiation, to be able to explain how an object's temperature affects the type of radiation it gives off. There's a few key laws there. And then talk a little bit about the type of radiation the sun gives off versus the type of radiation that Earth gives off. And actually even the fact that, yes, the Earth does give off radiation. So let's jump in. So what is radiation to begin with? Well, radiation is the transfer of energy through open space or through almost any medium in the form of electromagnetic waves. So rather than using some kind of intermediate object or fluid, radiation uses electromagnetic waves, which are beams of energy. Now, unlike conduction, which needs that intermediate object, or convection, which needs that fluid, radiation needs nothing to travel through. It can travel through empty space, it can travel through water, it can travel through air, it can travel through many different types of media. Whereas, as I said, conduction needs a conductor, convection needs a fluid. Radiation can travel through all kinds of things. Now, with that said, there are three key properties of radiation: wavelength, frequency, and energy. And I'm going to spend a couple of minutes talking about each one. With that said, the kingpin of them all is wavelength. So what is wavelength? Well, if we were to zoom in and look at any beam of radiation, we would notice what looks like what's called a sine wave. A sine wave is basically a wave that goes up, peaks, goes down, bottoms out, goes back up, and peaks again. Well, the wavelength of a beam of radiation is simply the distance between one peak and the very next peak. So it's between two consecutive peaks. And so that's what the wavelength is. Now, the wavelength is extremely important because it determines everything else we need to know about radiation. Now, the primary unit we use for wavelength is what's called the micrometer. Beams of radiation have such tiny wavelengths that using the common units of distance that we use, such as inches, feet, meters, yards, miles, and so on, isn't going to cut it in this case. So we use what's called a micrometer, also known as a micron. 1 micron represents 1/1,000,000th of a meter. 1/1,000,000th of a meter. That is extremely tiny. That's 1/100,000th of a decimeter, 1/10,000th of a centimeter, 1,000th of a millimeter. So that's extremely tiny. If you think about a strand of your hair, the thickness of a strand of your hair is measured in multiple micrometers. So radiation wavelengths are commonly very short. As I mentioned a few moments ago, everything else we need to know about radiation is determined by its wavelength. And in fact, radiation runs the gamut of many different types of wavelengths. And we can look at that on what's called the electromagnetic spectrum. Now, the other two properties that I mentioned about radiation are also determined by the wavelength. Specifically, frequency and energy are inversely related to a wavelength. So think about this. Take a piece of paper and draw a wave on it. Just an up and down wave. If you were to decrease the wavelength of that one wave, you could fit more waves on that same page, which means that more waves would be occurring, hence the frequency would be higher. So the shorter the wavelength, the higher the frequency. On the other hand, the longer the wavelength, the lower the frequency. And this also relates to energy in that the longer the wavelength, the less energy. The shorter the wavelength, the more energy. And this is really important too because very long wave radiation has very low energy, such as AM radio waves. AM radio waves are many meters in distance, and they're very low energy. They pass through us harmlessly, nothing wrong. On the other hand, the shortest wave energy beams are alpha waves, gamma waves, and so on, and those are actually very, very high energy wavelengths. If we get pierced with any kind of alpha radiation or gamma radiation, we can actually experience substantial mutations, cancers, and even death. So really the wavelength gives us a lot of information about how energetic the different wavelengths of radiation are. Now the different types of radiation can be seen on what's called an electromagnetic spectrum. And this just gives us the gamut of all the different types of radiation and how they relate to wavelengths. The lowest energy radiation up here has the longest wavelength, and this includes AM radio waves and television waves, which, again, as I mentioned, pass through us harmlessly. On the other hand, ultraviolet waves, we know that those can give us sunburns. X-rays can pierce through our skin, get absorbed by our bones, and then emitted back out. And actually, this is what we can use to determine if we have a broken bone or a cavity in our teeth, or so on. And then in between, we have things such as microwaves, which are a special wavelength that water is sensitive to, infrared waves, and then visible light. So yes, believe it or not, all the colors you're seeing, including the ones on this screen, are actually radiation. They're radiation. Now, there's a few key things I want you to know about radiation, and these few key things are going to tell you a lot about different objects, the type of radiation they give off, and so on. And the first one is really not a law, it's actually a fact. The other two are actual laws. So the first one I like to jokingly call Oprah's Law. And the reason why I call it Oprah's Law is, well, you'll see in a second. So this fact is that every object that has a temperature above absolute zero emits radiation. So think about that. Look around your room right now or wherever you're at and think about all of the objects in that room. This computer in front of you or this mobile device that you're on. Think about the textbook, or think about your phone. Think about the chair you're sitting on or the bed you're sitting on. Think about everything. Every one of those objects emits radiation. And so do you. And if you see somebody else, point at them and say they emit radiation. And then find somebody else and they emit radiation, and so on. In fact, everybody emits radiation. That's why I call it Oprah's Law. Because everything and everyone with a temperature above absolute zero, and this means everything on Earth, emits radiation, including you. That's why I call it Oprah's Law. Again, that's not the technical name. You're not going to be tested on that name. But know the fact that everything with a temperature above absolute zero emits radiation. Now, obviously, we're not emitting gamma rays and giving each other cancer, or we're not emitting microwaves and cooking each other. So what type of radiation do we actually emit? Well, to figure that out, we're going to look at the other two laws. The first law we're going to look at is what's called Wien's law. Wien's law states that the wavelength emitted by an object depends on the object's temperature. And here's how Wien's law actually works. Wien's law is a simple equation. I won't make you memorize it, but it's there if you want it. And what it states is lambda max equals 2897 divided by T. Now, lambda max, this is just a fancy symbol for the most commonly emitted wavelength. Lambda is a symbol that we often use to denote wavelength, and max means the one that just emitted the most. So the radiation that an object most commonly emits is called lambda max. And we can calculate this wavelength simply by using this constant dividing by the object's temperature in Kelvin. And that can tell us the wavelength. The warmer this temperature is, the shorter the wavelength is going to be. As you know, the higher a denominator is, the smaller the overall fraction is. So most of the radiation that an object gives off is around that lambda max. And this actually explains why certain hot things glow. Because they become so hot. They become so hot that they actually begin to emit visible light. Whereas on the other hand, colder things like us as humans, we actually emit what's called infrared radiation. We emit much longer wavelengths. So unfortunately, you can tell all your friends that your teacher said that you're radiant because, according to quote-unquote Oprah's law, you emit radiation. You're not warm enough, temperature-wise, to actually be glowing. And so that's why you don't glow. Now, not only does temperature determine the type of radiation you give off, temperature also determines how much radiation you give off. This law is what's called the Stefan-Boltzmann law. And it's summed up in this equation here, which again, I don't want you to memorize it. You're not going to have to calculate with it. But let me explain what each one of these things means. This E over here on the left represents total amount of energy. This little weird looking symbol here, this is the lowercase sigma. This is what's called the Stefan-Boltzmann constant. And then this T to the fourth is simply whatever the temperature is raised to the fourth power. So you could actually calculate this. If I gave you this number and you had a calculator, you could knock it out real fast. But all I really want you to know is the warmer the object, the more radiation it emits. And as we learned from Wien's law, in shorter wavelengths. So warm objects emit lots of radiation in short wavelengths. Now the opposite is true too. The colder the object, the less radiation it emits. And it emits it in shorter wavelengths, in longer wavelengths. In longer wavelengths. Now, with this said, there's some important things I want you to know about the sun and the earth. And really, as we talk about radiation in the future days and weeks to come, these are really going to be the crucial things that I want you to know. So, first, let's talk about the fact that, according to Oprah, both the sun and the earth have temperatures above absolute zero. So they both emit radiation. So yes, believe it or not, the earth right now is emitting radiation. Well, as you are, as all the objects around you are. Now, the sun has an average temperature at the surface of 6,000 Kelvin, which is about 10,500 degrees Fahrenheit. That's really hot. And because it's so hot, it emits a lot of radiation. And it emits it primarily in short wavelengths. And the short wavelengths it emits are ultraviolet, visible light, and near-infrared radiation. So most of the sun's radiation comes out in these three forms. We have a fancy name for this, and it's one I want you to memorize. We call it shortwave radiation. So the sun emits shortwave radiation, and because the sun is so hot, it emits a lot of it. On the other hand, the Earth has a much colder temperature. Its average temperature is only 288 Kelvin. And remember, Kelvin is based off of absolute zero, so that might seem like a big number. It's really not. So the Earth has a temperature of 288 Kelvin. And it emits primarily infrared radiation. And it emits it in the wavelengths of somewhere between 5 to 20 microns, whereas the sun, most of its radiation is between 1/10 of a micron to 1 to 2 microns. So the Earth emits much longer wavelength radiation, and it emits a lot less than the sun does. Overall, we call this long wave radiation. So the sun emits shortwave radiation, the Earth emits long wave radiation. Hold on to those two terms because we're going to use them a lot for the duration of this quarter. Got it? Well, let's move on real quick. And solar radiation consists of three main things, as I mentioned. About 7% is ultraviolet and lower wavelength, so X-rays, gamma rays, and so on. Primarily ultraviolet, UVA, UVB, UVC. On the other end, 48% is near infrared, and then a little bit more on the far infrared. But the majority, well, the most commonly emitted radiation falls under visible light. This is why our sun glows. Our sun glows because the most common radiation that it emits is in the visible light spectrum. And that's why our sun looks so bright and gives us sunlight, and that's why it illuminates our days, because it's emitting a lot of visible light. Now, when we compare this to the Earth being a lot colder doesn't emit nearly as much radiation. And the radiation it does emit is in much longer wavelengths. Hence, I'm sorry, Earth doesn't glow. And neither do us. We're just not hot enough. So, with this said, here's how this whole process works. And this is the last thing I'll mention before we move on into some other interesting things in the next few lectures. But the way this all works is we start with our sun, nice and hot, temperature of 6,000 Kelvin, and it shoots off shortwave radiation to our Earth. Now, as our Earth absorbs this radiation, the temperature of our Earth warms up. Now, per the Stefan Boltzmann law, the warmer an object is, the more radiation it gives off. So as the Earth absorbs heat from the sun, the Earth begins to give off additional long-wave radiation. So sun heats the Earth up, sun emits radiation, Earth absorbs it, Earth heats up, Earth gives off more long-wave radiation. And it's the balance between incoming shortwave radiation and this outgoing long-wave radiation that ultimately plays a key role in everything that happens on Earth, such as when the warmest time of the day is, or how cold it gets at night, or how do clouds impact all of this? Why is it hotter in the summer and colder in the winter? So all of those things all come back to this fundamental balance between incoming shortwave radiation and outgoing longwave radiation. Now that we'll talk about next time. So until then, I'm Terrence Mullins. Thank you for listening.